Hi, I'm Miss Hall.
Hi, I don't remember.
Okay, we can do it again. Hi, I'm Miss Hall.
Hi, I'm Miss Isaac. Hi, I'm Miss Ethan,
And this is lesson 97. Reject or accept a hypothesis. Statisticians use a confidence interval to express the degree of uncertainty associated with a sample statistic. A confidence interval is an interval estimate combined with a probability statement. For example, suppose a statistician conducted a survey and computed an interval estimate based on survey data. The statistician might use a confidence level to describe the uncertainty associated with the interval estimate. The statistician might describe the interval estimate as a 95% confidence interval. This means that if we use the same sampling method to select different samples and compute an interval estimate for each sample, we would expect the true population parameter to fall within the interval estimate 95% of the time. A 95% confidence interval comes from the normal curve, 2 standard deviations from the mean. A 95% confidence interval is approximately equal to the interval of a margin of error on either side of the mean. This is what we did in the previous lesson. On a normal curve, we can say 2 standard deviations from the mean is your 95% confidence interval. So if this is the mean, here are 2 standard deviations. Inside these 2 standard deviations fall 95% of the data. When we calculated margin of error, the formula from yesterday, we found that formula was plus or minus 2 radical p times 1 minus p over n. That was calculating 2 standard deviations on either side of the mean. Example 1. 55 students attending the prom were randomly selected to participate in a survey about the music choice at the prom. 60% respond that a DJ would be preferred over a band. Members of the prom committee thought the vote would have 50% for the DJ and 50% for the band. A simulation was run 200 times, each of sample size 55, based on the premise that 60% of the students would prefer a DJ. The approximate normal simulation results are shown. Using the results of the simulation, determine a plausible interval containing the middle 95% of the data, rounding all values to the nearest hundredth. This is approximately a normal distribution curve. The mean, we're actually given the mean. The mean is 0.602.
And let's work to understand what this mean is of. This mean is of it's the value calculated for the 200 simulations. So we had a computer run 200 simulations with a sample size of 55 in each, and what came up is the survey proportion, the percent of people who preferred the DJ. So this mean is when we run this simulation, the mean says of all of these means, it's actually called the mean of the sample means. It says 60% of the time, 60.2% of the time, not percent of the time, excuse me. The proportion of students who preferred a DJ was 60.2%.
Right. So what happens with this simulation is they have 55 students, and for each student, 60% of the time they're like a yes, but 40% of the time they're a no. So they go through for these 55 students, right? And so not exactly 60% will say yes, because sometimes, like, isn't it like rolling a 10-sided die for every student? And if they get 1 through 6, they're a yes, they prefer the DJ. If they get 7 through 10, no, They prefer a band. So for every student, this imaginary die is rolled. And so 60% of the time, each student is going to say yes, but it's not perfectly 60% of the time because there's some randomness thrown in.
Yeah, I never thought about it that way. I thought of, like, in the 55 students, we're just kind of like grouping them differently. But no, your way makes sense.
Right. And so then your you're doing this roll of 55 students and calculating.
You're doing a 10-sided die roll for 55 students, and then you're doing that 200 times.
Mm-hmm.
Right? And so any 1 through 6s are a yes, any 7 through 10s are a no, and we're calculating the proportion of yeses of those 55 students for every simulation.
Right, 200 times. Okay, so the mean is 0.602. Well, that makes sense because 60% of the students said
that
yes.
We surveyed, yeah.
Right, of the 55 that we surveyed said yes. So, like, in this simulation, 60% of the time people, or like 60% of the group want yes. And now if I wanted to calculate 2 standard deviations on either side, isn't it convenient that it tells me right here what a standard deviation is?
Oh, so we don't have to use that margin of error formula from yesterday.
No.
We just use...
It's so hard to read. Is it 6? Yeah. Oh, this is a mistake.
Yeah. That's only 1 standard deviation away. If we want to calculate the 95% confidence interval, we need to move 2 standard deviations away from the mean. Can we maybe, well, we'll show that on the curve after we calculate it.
Okay.
Oh, why are you stopping after 2? Oh, it said round all values to the nearest hundredth. Okay.
So that is 0.47 and 7.3.
0.73.
0.73. And so this is 95% of the data. And
there's kind of a great check here. Do these values make sense? Well, look at the bell curve that we just drew. Does that look like about 95% of the surveys had a mean within 0.47 and 0.73? A proportion between 0.47 and 0.73. It does.
Okay. So you could alternatively use the formula from yesterday, where, you still need the mean though. So you need the 0.602, and then you plus or minus 2 square root of 0.60 times 0.40, or 1 minus 6, all over 55.
And that's actually the number they calculated. That gives you the 0.066. Doesn't it? Oh, no, it doesn't, does it?
Well, no, because you multiply it by 2.
Oh, it does. Yeah, it does.
And so when you round, you also get 0.47 to 0.73. Example 2. Gabriel performed an experiment to see if planting 13 tomato plants in black plastic mulch leads to larger tomatoes than if 13 plants are planted without mulch. He observed that the average weight of the tomatoes from tomato plants grown in black plastic mulch was 5 ounces greater than those from the plants planted without mulch. To determine if the observed difference is statistically significant, he re-randomized the tomato groups 100 times to study these random differences in the mean weights. The output of his simulation is summarized in the dot plot shown. Given these results, what is an appropriate inference that can be drawn?
So I think very basically, we might say, and this might be something you've done in a science class previously, you might say, well, obviously the black plastic mulch had an effect because it's 5 ounces greater. And so my initial reaction without any statistics knowledge is choice 3, that there's strong evidence to support the hypothesis that tomatoes from plants planted in black plastic mulch are larger than those planted without mulch. That's what I would think at first, and I think a lot of people would support that, but that's actually incorrect when we look at the dot plot.
Okay, so you have these 13 plants that had the mulch, and you had 13 plants without. Right, so these had the black plastic mulch, and these did not. And these were 5 ounces greater, right?
Yep, the mean of those was 5 ounces greater.
So let me just give some numbers. So this was 25 ounces. The average weight of the plants in the mulch was 25. The average without was 20 ounces. Okay? And so now we're going to randomize those groups and split them into various groups of 13 and 13 and find the average of each of these random groups and the difference of those averages.
Right. So the difference of this are measured was 5. 25 minus 5. So this is the difference. It's a bad 5.
Okay. But then that's what this simulation is doing. And then what is the difference between these two? And so you see all these dots. So like here, the difference was 0.
And that's what we'd expect. If we just randomly pick these plants and put them into 2 groups, we'd expect to get around 0 because, you know, some of the plants will be big in this one, some of them will be small, and in the other group, some plants will be big, some will be small. But when we take their mean, all of that will average out and they'll get close together. So we expect most of the time for the 2 groups to have similar mean weights.
Okay. And so this is now, we're going to estimate the 95% confidence interval based on this graph. So I'm saying roughly here is the mean, and roughly here and here are 2 standard deviations. It's my estimate. Now I want to see if a 5-ounce difference falls within 95%. And 5 ounces falls right around here, which is within 95%. So it's likely that that could just happen by chance.
Yep. So remember, anything that happens within the 95% confidence interval is something that can happen randomly or normally. So it is very normal that if we group these tomato plants however we want to group them, we get a 5-ounce difference.
Okay, so there is not strong evidence to support his hypothesis. There was no effect observed between the 2 groups. Well, there was a 5-ounce difference effect observed. There was an effect observed that could be due to random assignment of the plants to the groups. Yes. It is likely when we re-randomize these plants in this simulation, like 5 ounces was within the 95%.
A difference of 5 ounces in the mean weights is somewhat normal. It falls within 95% of within our 95% confidence interval. So basically what we're saying is, although this one specific time when we grouped these tomatoes and we gave them the black mulch, we could have randomly picked a different group of 13 tomatoes that didn't have the mulch, and they might have been 5 ounces bigger. And that happens within 95% of the time, within that 95% confidence interval.